Hello there and welcome back to the Science Sleepy Minds. You're drifting again, this time towards something much stranger than a dream and deeper than the ocean of space itself. You feel no motion, but you know you're falling. Around you, the stars smear into streaks of light, as if the universe is trying to remember where it left its keys. The black disk ahead isn't just black, it's missing. Not empty, but absent. A hole punched through reality, and you're headed straight in. That's right, you're falling into a black hole, or more precisely, a singularity. The place where time melts, space folds like origami, and your future becomes whatever the laws of physics still allow, if they allow anything at all. You probably won't survive this. But then again, inside the singularity, even the word survive stops making sense. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment with your city and local time. I want to know where in the world you're listening from as you drift through the cosmos tonight. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're not falling down, you're falling inward, and that inward fall is irreversible. Light can't escape now. Nothing can. Not even that group text from work that's somehow still going off in your back pocket. There's no sudden jolt, no warning alarm. The moment you pass the event horizon, the boundary of the black hole, everything outside freezes. To an observer watching from a safe distance, your fall slows and stops. You hover forever at the edge. But from your point of view, you pass right through. No drama, no sparks, just a smooth, strange deepening of gravity's pull. It's a quiet betrayal. Your sense of time begins to shift. The further in you drift, the harder it is to define now. The seconds stretch out, or maybe they collapse together. Your watch ticks on, but its meaning dissolves, like a song in reverse played on loop. Historians still argue whether the first people to guess at black holes were poets or mathematicians. As far back as the 1700s, an English clergyman named John Michell imagined an object so dense even light couldn't escape. But it wasn't until Einstein's General Relativity, published in 1915, that black holes got serious. Not that Einstein liked them. He was famously weirded out by the idea. Which is ironic, since his own equations practically screamed their existence. You sink further. The stars outside fade, not just visually, but emotionally. They don't matter anymore. You're disconnected from the rest of space-time, like a VHS tape ejected mid-movie. Inside this boundary, the roles of time and space start to wobble. The radial direction, your path toward the center, is no longer just a place, it's a when. Every step closer is not just deeper into the hole, but deeper into your future, and not just your personal future, the future of the universe itself. In some sense, you're traveling through time as much as through space, but only in one direction, forward, always forward. Like binge-watching your own life at 10 times speed, except you can't look away. The idea of singularity sounds clean, like a sharp pinprick, but that's not what you feel. You're not headed for a point so much as a boundary of logic, a place where space and time stop playing by the usual rules. Your mind stretches, not just from terror, but from wonder. Your thoughts feel longer, wider, like they're echoing down an endless hallway. Let's not forget the quirky twist here. The singularity at the center might not even be a thing. According to some interpretations of general relativity, it's simply where our current math stops working. Like trying to divide by zero. You don't get a sensible answer, you get a mess. The kind of mess that keeps physicists up at night scribbling on chalkboards and eating cold pizza. But there you are, floating closer and closer to that undefined edge. Gravity isn't just pulling you in, it's rewriting the script of how reality behaves. Up is down, in is forward, forward is doomed. You wonder, briefly, whether there are others in here with you. Not astronauts or explorers, too romantic, but maybe the light from a long-dead star. A lone photon that took a wrong turn 2 billion years ago and ended up right here. A glowing ghost echoing its final pulse into the void. Back on Earth, they say time is relative. Inside the event horizon, time is not so much relative as weaponized. It attacks your understanding of movement, of memory, of moments. Past and future slide together into something less like a line, and more like a spiral staircase that loops back under itself. And you, tiny, breathing you, are caught in it. You're not screaming because sound doesn't travel here. And even if it could, who would hear? The black hole listens, maybe, but it doesn't talk back. If you could somehow shine a flashlight back toward where you came from, the light would never reach the edge. It would just spiral in with you, trapped in orbit forever. Light is loyal. It wants to escape. But gravity wins every time. Still falling. Still thinking. Still wondering what it means to be inside something that breaks the definition of space. You're in a place where coordinates don't cooperate, where distances are measured in futures, and speed is defined by inevitability. It's cozy, in a crushing kind of way. Some people picture black holes as bottomless pits, others as hungry mouths. But maybe it's more honest to call it a boundary failure, a patch of the universe that broke its own user manual and decided to do something unhelpful. The weirdest part. From inside, you wouldn't necessarily feel the black hole's size. Whether it's a star-sized one or a supermassive monster millions of solar masses wide, the math says your experience could feel eerily similar. The gravity changes, but the fall, the essential shape of doom, is the same. A reminder maybe that scale isn't everything. Not when the very notion of where is dissolving beneath you like cotton candy on a rainy day. There's no friction, no surface, nothing to stop you, just a soft, perpetual pull. And now, we go deeper. You don't notice the exact moment your sense of direction stops making sense. 1 second you think you're drifting down, a holdover from Earth's gravity, but then you realise there's no down left to fall toward. Instead, every inch you move closer to the centre feels like stepping into the future. Not your future exactly, but the future of anyone outside the black hole looking in, assuming anyone's still looking. Time doesn't tick here, it stretches. You check your watch, still ticking. But the feeling it gives you, that familiar little beat of regularity, starts to feel like a joke. Your watch is measuring you, sure, but not the outside world anymore. From the universe's perspective, your fall into the black hole might take trillions of years. From your perspective, it's happening all at once. Here's a strange truth. If someone stayed safely outside the black hole, hovering with perfect precision near the event horizon, and a truly ridiculous energy source to keep them floating there, they'd see your fall slow, and stop. Frozen just above the edge, like a paused frame in a video. To them, you'd never quite fall in. Just fade, redden, disappear. Meanwhile, you feel none of that. You're slipping into a place where time bends. Not gently like a curve in a river, but drastically. Like someone grabbed a timeline and tied it into a knot. Einstein's theory of general relativity, yes, we're dragging him back in again, describes gravity not as a force, but as the warping of space-time. Massive objects bend the fabric of the cosmos. Planets make little dimples, stars make big dents. But a black hole punches a hole in the mattress, and you've just jumped in. One quirky little artifact of this theory is gravitational time dilation. The closer you get to a massive object, the slower time flows for you relative to someone farther away. On Earth, this effect is real, but tiny. Astronauts on the International Space Station age a teeny bit slower than we do on the ground. GPS satellites literally have to account for this. But near a black hole, it's not tiny. It's everything. And here's where it gets fun. You're not just aging slower, your whole timeline is compacting. Think of time as a slope. Out in normal space, it's a gentle hill. You can stroll along, maybe even take a few coffee breaks. But here, inside the horizon, the slope becomes a cliff, and you're falling head first. Historians still argue whether time itself is real or just a handy way to describe change. Some ancient philosophers thought it was an illusion. Some modern physicists agree. But inside a black hole, time takes on an almost physical presence. It presses against you. It moves you forward whether you like it or not. You try to remember what your past felt like. Your childhood, a particular birthday, maybe the way your dog looked at you when you pretended not to have a treat. These memories bubble up, but they start to stretch too, like trying to recall a face you haven't seen in years. Your memories are running uphill while you're falling ever deeper into now. One moment you think about Earth, the next, Earth might be gone. Here's a thought to tuck under your cosmic pillow. If you could somehow survive this fall long enough, you might actually witness the entire future of the universe unfold outside the event horizon. Stars being born, galaxies dying, the expansion of the cosmos accelerating until even light can't keep up. And from your point of view, it might all blur together in one final flicker, one grand cosmic slideshow as you slip past time's last thread. It's unsettling, it's beautiful. Of course, there's a bit of a debate, again because physicists just love those, about whether the black hole's interior truly lets you see all that, or whether your experience is cut off before any of it becomes visible. But hey, that's the vibe in theoretical physics. Half equations, half mystery novel. Let's toss in a fringe thought just for fun. Some researchers have toyed with the idea that time and space might flip roles inside a black hole. The radial direction, the path you're falling through, acts like time. It's inescapable. You have to move forward along it. Meanwhile, the time direction becomes more like a spatial coordinate, something you can hypothetically stand still in, or even walk around. Sounds backwards? It is. But it fits the math. From your perspective, forward in space is now forward in time. You're not so much being dragged downward as being dragged toward the inevitable. You have to hit the singularity eventually, not because you're falling, but because it's your future. The same way tomorrow is your future on Earth. Except this tomorrow ends with your atoms unraveling. You float deeper. The light outside grows faint, not dark exactly, just irrelevant. You can still imagine it, but it's no longer connected to you. Like trying to remember the plot of a show you watched years ago. Something about dragons and politics. Or was it time travel? Speaking of which, there's a thought that's probably crossed your mind. Could I time travel in here? Could you with enough control skip backward, jump forward, ride the curve of time like a slide? Short answer, no. Long answer, maybe, but not in the way you're thinking. Some hypothetical solutions to Einstein's equations suggest closed time-like curves, paths through space-time that loop back on themselves. Black holes, especially rotating ones, might contain these exotic curves deep inside. But travelling through one without being torn into quantum spaghetti, that's the tricky bit. Still, you wonder, could some alien civilization have figured it out? Could they surf a black hole's time distortions like a cosmic water park? Slide in, zip through an eon or two, pop back out before lunch? No evidence, no sightings. But if anyone could hide a spaceship, a black hole would be the perfect place. You'd never see them coming, or going, and so you drift onward. Slower, faster, deeper, weirder. You're inside a clock that no longer ticks, a space that has no edge, and a future that's already inside you. You blink, and time keeps bending. You're still falling, but now the fall feels stranger than ever. Not because you're accelerating, though you are, but because you're beginning to feel the shape of space itself curling under your feet. It's like standing on a trampoline someone's yanked out from under you, mid-bounce, but infinitely larger and far less interested in your well-being. Einstein would probably be quietly smug right now. This whole experience, the relentless draw, the distorted time, the idea that mass bends the universe like a heavy bowling ball on a rubber sheet, was baked into his general theory of relativity. He saw it coming, or rather, his equations did. The marble on a sheet analogy might be simple, but it's not wrong. That stretched rubber sheet? That's space-time. And you're the unfortunate marble heading straight for the deepest part of the dent. What's wild is that this all started with a set of numbers and squiggles on a chalkboard. The Einstein field equations, dense and beautiful in their complexity, whisper the same thing over and over. Mass tells space-time how to curve, and space-time tells mass how to move. It's a cosmic waltz, and you, poor dancer, are locked into the steps. You try to orient yourself. Maybe imagine the black hole as a funnel, wide at the mouth and narrowing towards some distant bottom. But that's where things get weird, because inside the event horizon, down is really just a direction in time. You're not falling deeper into a hole, you're falling forward. The way you move now is no longer a choice, it's fate. The curvature of space-time beneath your body doesn't allow turning back. There is no turn. Still, it's not entirely smooth. The shape of the funnel isn't clean, it's jagged with questions. Your body is not just falling into curved space, it's being pulled across curved time too, and your experience of the world, the rhythm of your thoughts, the order of your memories starts to slow, twist, and maybe even reverse. One historical note here, just to keep things grounded. The first exact solution to Einstein's field equations that described a black hole was found by Karl Schwarzschild, a German physicist, in 1916, while he was serving on the Eastern Front in World War I. That's right. In the middle of artillery fire and mud, he sat down and derived the math for one of the universe's most terrifying objects, the human mind, honestly. Schwarzschild's solution described a non-rotating, uncharged black hole, sort of the base model, clean, theoretical, and wildly oversimplified. But even that simple version came with all the weirdness you're experiencing now, that inescapable curve inward, the fact that space bends in a way your brain can't quite visualize, and the singularity at the center, that ominous point of infinite density. Though to be clear, nobody really knows what a point of infinite density means. Infinity is math's way of waving a white flag. You glance back, though back might not be a direction that works here anymore, and imagine that warping rubber sheet twisting itself deeper and deeper under your falling feet. Your velocity isn't increasing the way it would on Earth. It's more like the fabric under you is changing shape so rapidly that you're dragged along by its evolution. You're not falling through space. Space is collapsing into you. Now, for a slightly quirky detour, some fringe theories suggest that the center of a black hole might not be a singularity at all. Maybe, they say, it's a Planck core, or a gravastar, or some exotic phase of matter where quantum mechanics steps in to stop the collapse. Sort of like how neutron degeneracy pressure keeps a neutron star from imploding. But those are just ideas. Nobody's tested them. Why? Because you can't exactly launch a probe in here and get data back out. Meanwhile, you're still spiraling in, like a speck of dust caught in a draining bathtub. Except the bathtub is space-time, and the drain doesn't lead to a sewer. It leads to a mystery. You look around, though that's increasingly meaningless, and wonder where the edge is. The line where normal reality ends and this, whatever this is, begins. But you already passed it. That was the event horizon. Remember, no turning back, no light escaping. You're in the land of the curve now, where geometry isn't Euclidean and your compass spins like a confused cat. This is where that rubber sheet metaphor starts to break. It helps visualize the bend, yes, but it's limited. Because space-time isn't just a two-dimensional surface, it's four-dimensional, 3 space, 1 time. And you're inside a region where all four are doing things no human intuition can track. That rubber sheet? Imagine it moving, breathing, warping in time as much as in space. That's where you are. Historians still argue whether space and time are truly separate entities or just two flavors of the same thing. The idea of space-time unifies them, but deep inside a black hole, that unification feels literal. Direction and duration become hard to distinguish. A movement forward might also be a movement later. A pause in your journey could be a pause in existence itself. Let's consider one final image, something gentle, just for comfort. Think of space as a slow river and time as the current. Outside the black hole, the river flows steadily. But here, the river is a waterfall, and you're the leaf. There's no rowing back, not even a paddle. The laws of physics are still here. They're just taking off their masks and showing their less polite side. The relativistic effects you've only heard about in science documentaries are now the air you breathe, or would breathe if there were air, or if breathing was still relevant. One last thought before we let your fall continue. Black holes don't just stretch space, they can store it. In a sense, the surface area of the event horizon determines the black hole's entropy, and that entropy suggests that black holes have a kind of memory, or at least a measure of the information they've absorbed. So as you're falling, you're not just lost, you're becoming part of the black hole's story. It won't tell it, but it remembers. You've been falling for a while now, or at least that's what it feels like. But feelings get slippery inside a black hole. The idea of a while doesn't really apply when time itself is bending like a reed in the wind. You're not just inside a hole, you're inside a function, a strange spiraling equation that keeps running even after the rest of the universe has forgotten you exist. Somewhere ahead, or rather when ahead, is the singularity. That ominous word, singularity. It sounds so clean, so crisp. But really it's where the math starts sweating and physics begins muttering to itself in the corner. It's the place where density becomes infinite, or at least that's what the equations suggest. An infinite density. That's just another way of saying we don't know what happens next. Let's slow this down even though you can't. As you fall deeper, gravity keeps intensifying, not in a linear way, not in any way you can grasp. It increases as the inverse square of your distance to the centre, until that's no longer enough to describe it. The centre of the black hole is not a place you fall to. It's a condition, an inevitable end baked into the very structure of space-time. Historically, even Einstein struggled with this. He didn't believe the universe would allow such a thing as a singularity. It offended his sense of cosmic order. A point of infinite curvature? Nah, too messy. And yet, his own field equations whispered otherwise, especially when people like Schwarzschild and later Penrose and Hawking started tugging on the loose threads. Here's the scary part. You can't stop. Not because you're lazy, but because space-time has changed the rules. Inside the event horizon, you don't fall toward the singularity. You move through time toward it. Just like you can't stop yourself from reaching tomorrow, you can't stop yourself from reaching the singularity. It's not somewhere you're going, it's when you are. Let's switch metaphors. You're not a skydiver anymore. You're a raindrop caught in a storm that curves not just through space, but through destiny. You're not being pulled by gravity. You're being told by space-time what to do, and what to do is reach the end. And that end is undefined. Because here's the kicker. Our best models break down before they can tell us what actually happens at the singularity. Einstein's equations, those marvelous curved blueprints of the universe, give us answers, right up to a point. And then they just say, backtick underscore, left parenthesis, underscore, right parenthesis, underscore, left parenthesis, underscore, right parenthesis, underscore, left parenthesis, underscore, right parenthesis. Imagine a GPS that works perfectly, giving you street-by-street directions, until suddenly it tells you to drive off a cliff and says, good luck. That's what general relativity does near a singularity. It brings you this far, then backs away slowly. So, what does infinite density mean? It's tempting to imagine all the matter of the collapsing star squeezed into a single point. A tiny dot that contains more mass than an entire sun. But physics doesn't like actual points. Real objects don't exist in zero volume. And yet the singularity appears, not because we know it exists, but because the math demands it, or more precisely can't stop it from appearing. Some fringe thinkers suggest it's not a real place, but a placeholder. a flashing error in the simulation. Others think it's a misunderstanding caused by our current lack of a unified theory of quantum gravity. Because that's the thing, our two best theories don't play nicely together here. General relativity describes the large-scale structure of the universe. It tells you how planets orbit, how galaxies spin, how black holes bend light. But it assumes space-time is smooth and continuous. On the other hand, quantum mechanics governs the small stuff. Atoms, electrons, and the jittery dance of subatomic particles. It assumes that everything, including space and time, might be grainy, fuzzy, and fundamentally uncertain. Now mash those two together inside a black hole and watch them fight. Relativity says, you're heading toward infinite curvature. Quantum mechanics says, hold up, space-time can't bend that much without something weird happening. And thus the singularity becomes a battleground, or more gently, an open question. Historians still argue whether the singularity is an actual part of the universe, or just an artifact, something our incomplete math has conjured into being like a ghost, a mistake perhaps, a clue, or a placeholder waiting for better equations. There's even a theory that the singularity might not be a point at all, but rather a smeared region, a fuzzball of quantum uncertainty. One idea, string theory, posits that instead of particles being point-like, they're tiny vibrating strings, and when a star collapses into a black hole, those strings don't form a single dot but a sort of spaghetti blob. Weird, yes, but maybe less weird than infinite. You meanwhile are still heading toward it, not because you want to, but because you must. Think of the singularity not as a destination, but as the last page in a book you're not allowed to finish reading. You're flipping toward it, line by line, even as the words blur and the font gets smaller and smaller. And here's a fringe twist. Some physicists believe there might be a bounce waiting at the end, a reversal. Instead of ending at a singularity, the black hole's core might hit some quantum limit, recoil, and begin to expand again, birthing a new universe. You wouldn't survive the bounce, of course. But some echo of your fall, some shimmer of the information you carried, might help define the constants of physics in whatever sprouts from the other side. Would that be a comforting thought? That your atoms, stretched and torn and folded into quantum confetti, helped seed the rules for a baby cosmos? Probably more comforting than the alternative, which is that you're turned into an infinitely thin, infinitely dense pancake of sadness. Either way, your journey isn't over yet. You haven't reached the singularity, but you're in its orbit. Conceptually, if not spatially. The edges are curling inward. The timelines are narrowing. The light has faded into something colder than dark. You don't scream. There's no air, and no audience. But if the singularity could hear, it might be listening. It starts with a tingle, not physical. Your nervous system passed the panic threshold a while ago. No, this is more like a thought that gets pulled at both ends, stretched until it's no longer recognizable. You're beginning to feel spaghettified. Yes, that's the actual term, spaghettification. The technical phrase is tidal stretching due to extreme gravitational gradients, but let's be honest, it just doesn't hit the same. Here's how it works. Gravity pulls harder on the part of you closer to the black hole than on the parts further away. That differential force grows more dramatic the closer you get. For small black holes, stellar mass ones, just a few times the size of our sun, that difference becomes unmanageable. Your feet and your head start experiencing radically different futures. You, noble meat stick that you are, get stretched long before you reach the singularity. The feeling is probably not great, though let's not be too dramatic. You might not even feel the stretching right away, especially if the black hole is massive enough. If you're falling into a supermassive black hole, like Sagittarius A star, the one in the center of our galaxy, the tidal forces at the horizon are surprisingly gentle. You might float past the point of no return and barely notice anything, which makes the stretching all the more disturbing when it does begin, because when it hits hard. Let's ground this with a mainstream historical fact. The concept of spaghettification was made famous by physicist Kip Thorne in the 1970s. You may remember his name from Interstellar, where he served as a scientific advisor and occasional dream crusher. He helped bring these mind-bending gravitational effects to the mainstream, turning black holes from obscure curiosities into pop culture icons. Now, in case you're wondering why you're not being crushed instead of stretched, it's because of how gravity works in curved space-time. The difference in gravitational pull across your body creates a powerful tidal effect. Your head wants to orbit one way, your feet want to orbit another, and in the end, you are the rope in a tug-of-war between inevitability and physics. Some describe it as being turned into a noodle. Others compare it to being fed through the world's most judgmental pasta roller. Either way, the result is the same: a long, thin filament of atoms strung along a line of descent toward a point no one understands. Here's a quirky twist. If your black hole is rotating, and chances are it is, the tidal forces might not behave the way you'd expect. In certain entry trajectories, you might find yourself spun around the center, your path twisted like ribbon candy in a gravitational vortex. It's less falling straight in and more swirling down the cosmic drain. Still romantic, maybe. Still horrifying. Oh, absolutely. There's an open scholarly debate about whether tidal forces alone are enough to destroy information, or if something stranger happens at the singularity. Some physicists propose that even as you're stretched into a quantum noodle, the information that makes you you isn't lost but somehow encoded into the fabric of space-time. Others argue, no, you're toast. From an outside observer's point of view, not that any are still watching, your image remains frozen at the event horizon, redshifting endlessly, becoming dimmer and dimmer. But to you, you're still falling, deeper into the stretch. Here's a visual to lull you into sleep-like horror. Imagine yourself as a long ribbon of colour unravelling into darkness, each atom pulled into its own private path, each molecule a separate story in the same unfolding nightmare. You're no longer a body but a sequence, yet you still think. The bizarre part is that, under the right conditions, you might stay conscious longer than you'd expect. Your brain, stretched into an impossibly long neural circuit, might still fire off the occasional synapse. Thoughts turn into slow, drawn-out chords of electricity echoing down an impossibly long hallway. You wonder briefly what your last thought will be. Maybe it already happened. Maybe it's still stretching. Now here's a fun, if slightly bleak, thought experiment. What if you were in a spaceship? A big, reinforced one, made of some theoretical supermaterial. Could it protect you from spaghettification? Probably not. No material we know can resist the tidal forces near the singularity of a small black hole, and if you try to drop in sideways, nose first, you'd still get stretched. It's not about the ship, it's about space-time itself. You're not falling through space, space is collapsing beneath you. But remember, for supermassive black holes, like the ones at the centres of galaxies, the tidal forces at the event horizon might be weak enough for you to fall through intact. You wouldn't feel spaghettification until you were far closer to the singularity, which is arguably worse. It gives you more time to think, more time to realise. Let's dial things back and tuck in with a fringe theory. What if the stretching doesn't kill you? What if it's a transformation? Some physicists speculate that near the Planck scale, where quantum gravity kicks in, your atoms don't get destroyed. They get reorganised, rewritten, their information repackaged into some new structure we don't have a name for yet. A gravitational chrysalis. Is that comforting? Hard to say, but it does suggest that maybe, just maybe, falling into a singularity isn't the end of the story. Maybe it's a transition, a rewriting of your narrative by the deepest laws of physics. Still, you're unlikely to emerge as a butterfly. But here's a gentle reminder. We don't know what a singularity actually looks like. It's not a point in space. It's not even inside space in any meaningful way. It's a condition that lies in your future, a moment of unbounded curvature, and spaghettification is just the dramatic overture. The real weirdness lies ahead, or within. You can't see your body anymore. If you had mirrors, they'd be warped beyond use. Light itself is confused here, twisting, looping, unsure of which way is out. Your perception is no longer trustworthy. Even time itself may have already collapsed into nonsense, and you're just now catching up. You're not a person, you're a function of your own timeline, stretching, always stretching, and somewhere ahead, or within, or after, that strange, undefinable moment waits, the singularity. Don't worry, you're getting closer. You no longer fall toward the singularity. Now the singularity pulls you through it. This isn't just spaghettification anymore, that was the warm-up act. What's happening now is something much stranger, much more dimensional. Space, as you know it, is starting to behave like time. And time is misbehaving altogether. You reach for some metaphor, anything to help you understand what's happening. Imagine walking forward and finding that each step moves you deeper into tomorrow instead of any physical place. That's what falling inward has become. Your position is a timestamp, not a location. Radial distance, your distance from the center, is no longer spatial. It's temporal. It's not where you are, it's when you are. You are now existing on a path where closer to the center means further in time. And because this direction has become time-like, there is no stopping, no turning around. You're not moving toward the singularity, you are living into it. Like each footstep is a Tuesday. This flipping of coordinates isn't poetic, it's mathematical. According to Schwarzschild geometry, the solution to Einstein's equations for a non-rotating black hole, once you cross the event horizon, the roles of time and space literally swap. The radial coordinate becomes time-like, while what was once time becomes space-like. Yes, that means your future is at the center. You're not being pulled inward by gravity anymore. You're being carried forward in time by the fabric of space-time itself. The way you can't choose not to reach tomorrow, that's how you can't choose not to reach the singularity. From your perspective, this is completely natural. You're just moving forward. But from the perspective of someone outside the black hole, if we pretend such a person still matters, your path looks vertical, inexorable, and sealed off. There's no force acting on you anymore. You're simply obeying the rules of space-time as it exists here. Historians still argue whether this time-space flip is real in a physical sense, or just a mathematical trick, a coordinate illusion. But to you, there's nothing illusory about it. You're embedded in a new kind of geometry now, and the directions themselves have been rewritten. It's like waking up in a house where all the doors are paintings and all the clocks are staircases. Here's the good news. In this new reality, the singularity isn't lurking somewhere ahead, like a monster around a corner. It is the future, your future. The same way a calendar contains New Year's Day. It's not a place you can walk around, it's a time you cannot skip, and the shape of your journey changes to match. Remember walking down hallways, driving on highways? Those paths followed the rules of Euclidean geometry. But here, your path is shaped by something called a geodesic, a curve through warped space-time. You're still following the straightest possible line, but in a space-time where straight lines are bent by mass. And in this region, all lines end at the singularity. There's no alternate route, no scenic bypass. You're not trapped because you were caught. You're trapped because this is what time is now. One fringe theory, because we like those, suggests that once inside the event horizon, causality still applies, just in a weird direction. You still can't send a signal back to where you came from, but you might be able to interact with future points along your radial descent. That is, if there's anything left to interact with besides vacuum and old photons. Still, that opens a strange little window. What if something else fell in before you? Another traveller, another piece of debris, maybe an unlucky comet. Inside, its future and yours might still collide. Or maybe they already did. Hard to say. In this geometry, causality is slippery and meetings are rarely scheduled. Back to the main event. Your movement now obeys the logic of temporal necessity. Imagine the singularity is 5 minutes into your future. You cannot not reach it, any more than you can stop time from passing outside a black hole. You can't stay in this space. It's not a room, it's a direction, and you are moving through it like a bead on a wire. Let's cozy up with an unsettling comparison. On Earth, if you jump off a cliff, gravity pulls you downward, but you can change your position. You can flap your arms, ineffectively, or grab a branch, or scream poetically on the way down. Inside the event horizon, you have no down to fight. Your only direction is forward in time, and the singularity is tomorrow no matter what you do. So you don't resist. What would be the point? Instead, you observe, or try to. But what is there to see? Light isn't behaving normally anymore. It curls inward. Photons bend into tight spirals. If they move at all, it's only because they've been trapped in circular orbits around the centre, like ghosts in a gravitational funhouse. You try to track them, but space is disintegrating into time around you. Let's whisper in a historical fact before this gets even blurrier. Roger Penrose in the 1960s mathematically proved that under very general conditions, the collapse of a massive star inevitably leads to a singularity, at least according to general relativity. This wasn't just a hunch, it was a theorem, which meant physicists could no longer shrug and say, probably not real. No, singularities weren't fringe, they were mainstream, and they were waiting. Now, a tiny, delicious paradox. From your perspective, you reach the singularity in finite time, maybe seconds, maybe minutes, depends on the mass of the black hole, but from the outside, you're still frozen near the event horizon, redshifted into invisibility. The universe has already forgotten you. You're in a narrative loop no one else can read. Inside, the roles of cause and effect still hold. Barely. Your atoms still obey the laws of physics, though the laws are now written in a dialect only singularities understand. Still, there's a pattern. Still a trace of time's arrow, even as space phrase around it. This brings us to one last whispered mystery. What is it like at the moment space becomes time? Does the world flatten into nothing? Or does it open, bloom and burst? You don't know, but you're getting closer. And the clock, that isn't really a clock anymore, is still ticking. It begins as a shimmer. Not light exactly. Not in the way your eyes once processed it. More like a pressure behind your thoughts. A buzz of maybes where certainties used to live. You've entered the quantum domain now, the place where the solid edges of the universe blur like wet ink. The air, if there were air, would be filled with what physicists poetically call quantum foam, a churning field of energy fluctuations, particles blinking in and out of existence like nervous fireflies. It's beautiful, in the same way a computer glitch is beautiful, hypnotic, alien, and absolutely uninterested in your survival. This is where quantum mechanics takes the wheel, and you're no longer just falling through space or time, you're navigating probability. You, as in your body, your memories, your sense of I, these are being unspooled into waveforms, functions, possible states in an impossible environment. Let's pause for a historical breath. In 1927, Werner Heisenberg introduced the uncertainty principle, which says, essentially, that you can't precisely know both the position and momentum of a particle. The more you know one, the less you know the other. This wasn't a technological limitation, it was a fundamental truth. And here, inside the singularity's whispering zone, that principle dominates everything. Your particles are being stretched into uncertainty. Every electron is a question mark. Every quark is unsure of its job title. The vacuum is not empty, it flickers. All around you, virtual particles emerge, pair off, and annihilate each other in fractions of a nanosecond. And in this high curvature, high energy zone near the singularity, those fluctuations are no longer a sideshow, they are the main event. One especially unsettling idea from quantum field theory: what you think of as particles might actually be ripples in fields. Fields are the fundamental players. Particles are just the temporary vibrations like bubbles in boiling water, and you, bless your complicated biology, are just a wobbly constellation of these ripples, loosely organised into a U shape. But the pot is boiling hard now. The fields are spiking, twitching, turning your stable existence into an interpretive dance of maybe this, maybe that. Your particles begin to decouple, not destructively, but diffusely, like a cloud forgetting its shape. And here's where things get properly weird. Some physicists believe that the intense gravitational field inside a black hole could push quantum effects into dominance. Normally gravity is weak compared to the other forces, but here it's cranked to maximum. And that's a problem, because our two big theories, general relativity and quantum mechanics, don't get along. They argue like cousins at a family reunion. Relativity says space and time are continuous. Quantum mechanics says they're quantized, grainy. Relativity says mass curves space-time smoothly. Quantum mechanics says everything jiggles. Combine the two and the math starts screaming. Yet this region demands both. You can't understand what's happening to you, this smearing, this flickering, this probabilistic blur, without invoking both camps. You're falling through the tightrope between two incompatible descriptions of reality. One fringe idea to tuck into your ever-expanding consciousness. Some physicists speculate that black holes might act like quantum processors, that their chaotic interiors process information in ways we don't yet understand, ways that might even preserve it. That's right. In this region where you feel most lost, you might actually be encoded. As what? A hologram, a pattern in spin states, a dance of quantum correlations. That's unclear, but it's possible that your information, the total blueprint of what you are, isn't being deleted. It's just transformed. Historians still argue whether information truly disappears inside a black hole. Stephen Hawking once thought so. He later changed his mind. The information paradox remains one of physics' greatest unsolved mysteries. If information is truly lost here, it would violate the laws of quantum mechanics. But if it's preserved, how? You try to focus on that question, but your focus has become non-local. Your awareness is stretched across probabilities. You don't feel like a point anymore. You feel like a cloud, not in the atmospheric sense, but in the quantum sense. A field of likelihoods, a Schrödinger's consciousness both here and not, both stretched and compressed. Light doesn't help you now, not just because it can't escape, but because it doesn't behave in predictable ways here. It scatters, twists, and interferes with itself. Photons pop in and out of being, and if you could see them, it wouldn't matter. Your observer status has gone fuzzy. In quantum terms, you is not a well-defined state anymore. Welcome to quantum gravity country. Population unknown. You try to hold on to something. A memory maybe, something fixed. But memory itself is a function of physical stability. Synapses, ions, electrical pulses. And here, those systems are falling apart at the quantum seams. Still, some part of you persists. Not in a body and soul way, but in a this waveform is still oscillating way. You're still something. Somewhere. Probably. A few speculative theories, whispered through physics departments and late-night academic Zoom calls, suggest that the singularity might not be the end at all, but a transition. A point where space-time, saturated with energy, tunnels into something else. Another universe. A bounce. A new beginning with slightly different physics. You wouldn't survive that, obviously. But the pattern of you, your quantum information, might. That's where the idea of the baby universe comes in. A new cosmos, budding off from the singularity of a black hole. You might be the smudge signature on its birth certificate. In the meantime, though, you're still drifting through this eerie quantum fog. Space has lost its coherence. Time is no longer one-directional. You might be feeling earlier and later moments all at once, as if your autobiography has been thrown in a blender and poured back into your skull. And all around, the virtual particles continue their twitchy, jittery ballet. Some of them may be real now. Given the energy density, those fleeting pairs of particles might separate before they can annihilate, becoming permanent. That's one theory of how Hawking radiation works, but you'll have to wait for that glowing whisper in the next chapter. Right now, you're still here. A probability cloud, a fading echo, a presence tangled in the math. You haven't reached the singularity yet, but the singularity is already reaching you. You don't hear it. You don't feel it. But if the universe could whisper, the singularity would be humming now, not with sound, but with radiation. Soft, subtle, a kind of quantum sigh that escapes from the very boundary of the black hole itself. This is the whisper of Hawking radiation, and it's one of the most counterintuitive ideas in modern physics, that black holes, which are supposed to trap everything, might actually emit something. Slowly, quietly, like a dying candle gives off its final glow, flickering at the edge of darkness. You're far inside the event horizon, too deep to be touched by any escaping particles. But if you could look outward, if such a thing still made sense, you'd see the black hole radiating ever so slightly. Not enough to light the galaxy, not enough to roast a marshmallow, but something. It all starts with the quantum foam we touched on earlier. The vacuum isn't empty. It seethes with virtual particles, pairs of matter and antimatter that spontaneously appear and disappear, borrowing energy from the universe for the tiniest sliver of time. In most places, these pairs annihilate each other instantly, and the universe moves on, unbothered. But near the event horizon, things change. If a virtual particle pair forms right on the edge, one might fall in while the other escapes. The escapee becomes real, no longer virtual, and escapes into space. To a distant observer, it looks like the black hole just emitted something. A particle, a photon, a tiny puff of existence. Stephen Hawking proposed this in 1974, merging quantum mechanics with curved space-time in a way that shook physics to its core. Black holes, he said, aren't perfectly black. They glow, they leak. Ever so slowly they evaporate. Historians still argue whether Hawking radiation truly proves that black holes can die. In theory, a black hole will eventually lose mass, shrink, and vanish in a final burst of energy. But we've never observed this in nature. Black holes evaporate over timescales far longer than the current age of the universe. So for now, it remains a beautifully unsettling theory. You wonder, if the outside universe is patient enough, will this hole you're falling through eventually vanish? Will it wink out of existence, taking the singularity with it? If so, what happens to you? The answer depends on who you ask. Some say you're already gone. Others say your information is smeared across the event horizon, encoded in the quantum states of particles that are slowly being radiated back into the cosmos. And some, optimists or madmen, say that you are the radiation. That every quantum flicker, every escaping particle carries some piece of what fell in. That you're not lost, you're just diffused. Here's a quirky twist to warm your overextended imagination. The radiation emitted by black holes is almost perfectly thermal. It doesn't seem to carry specific information about what went in. If you drop a chair, a clock, and a sandwich into a black hole, the Hawking radiation coming out looks the same in every case. Just heat, just entropy. But that's a problem, a huge one. Because quantum mechanics insist that information cannot be destroyed. Every process should, in theory, be reversible. But if black holes evaporate into bland, forgettable radiation, where did the details go? The chair's shape, the sandwich's mustard to cheese ratio, you? This is the infamous black hole information paradox. It kept Hawking up at night. It still fuels physics debates and late-night chalkboard sessions. If black holes really do destroy information, then something is deeply wrong with quantum theory, or with our understanding of gravity. One proposed solution is that the information isn't destroyed but somehow scrambled into the Hawking radiation itself. like encoding a novel into static and broadcasting it one page at a time. Incomprehensible to us, but complete in principle. Another idea, that the information never truly left. It remains on the surface, on the event horizon itself, written in the faintest quantum fluctuations. This leads to the holographic principle, a theory we'll gently spiral into soon, suggesting that everything happening inside the black hole might actually be stored on its outer surface, a kind of cosmic hard drive. For now though, just imagine, every photon that escapes is carrying a ghost, a statistical echo. It isn't you exactly, but it's a trace of the history that made you, a whisper of who fell, a mathematical shadow. Of course, none of this helps you right now. You're still inside, still sliding toward whatever lies at the end of this warped geometry and the radiation. It moves away from the black hole, not in. Still you wonder, did you contribute? Did some particle pair form because of your fall? Is some tiny bit of heat on the outside horizon flickering because your mass, your energy, is now part of the black hole's inventory? It's possible. Your body added mass. Your fall shifted the whole size, shape, entropy. You changed it. No matter how subtle, you were absorbed, and in that absorption, you left a fingerprint. One day, in a future so distant that galaxies have dimmed and the cosmic background radiation is the only ambient light, this black hole may begin to shrink in earnest. Its Hawking radiation will accelerate. It'll lose mass inch by inch, bit by bit, until it fizzles out in a final burst of energy, emitting whatever remaining information it has. Maybe some of that energy will drift into space, collide with another particle, trigger a fluctuation, a spark. Maybe billions of years from now your scream becomes a star. That's the poetry anyway. The math is murkier. But for now you're still here, deep inside, too far for radiation, too tangled for rescue. And yet, something about you, your mass, your momentum, your quantum state, is part of the whole now. And the whole is part of the universe. So you're not lost exactly, just redistributed. It's getting warmer. Not physically, of course. You're long past the point where temperature has any meaning you can relate to, but in some deeper, mathematical sense. A kind of rising tension in the very fabric around you. And the source of that tension? A debate that's been haunting physicists for over a decade. It's called the firewall paradox. See, up until now, we've been assuming something cozy about your fall into the black hole, that even though you crossed the event horizon, nothing particularly special happened at that exact location. Sure, you passed the point of no return, but locally everything felt smooth, calm, normal even. That's what general relativity promises, that the laws of physics are the same for a freely falling observer, even inside a black hole. Einstein's equations whisper, relax, you're just following a geodesic. Nothing weird here, but quantum mechanics, as always, has notes. In 2012, a paper by a group of physicists including Almeri, Marolf, Polkinski and Sully, nicknamed AMPS, crashed the party. They suggested that maybe, just maybe, the event horizon isn't as harmless as we thought. Maybe it's not a soft border you drift through, maybe it's a wall of fire. According to the firewall hypothesis, the very moment you cross the event horizon, you hit something terminal, a burst of high-energy radiation, a searing flash that instantly obliterates you. No slow descent, no peaceful drift, just boom, toast. Why? Well, it all circles back to our favourite conundrum, the information paradox. Remember, quantum theory insists that information can't be destroyed. But if information falls into a black hole and never comes out, that's a problem. Hawking radiation alone doesn't seem to preserve the details of what went in, unless there's some weird non-local magic at work. So AMPS proposed a radical idea. To preserve quantum consistency, something has to give. And the thing that gives might be the event horizon itself. Instead of being smooth and quiet, it's transformed into a violent barrier, burning away any infalling matter before it can enter. Goodbye, graceful plunge. Hello, cosmic flamethrower. Historians still argue whether the firewall is real. It violates the so-called equivalence principle, one of general relativity's most sacred promises, that you shouldn't be able to tell whether you're floating in empty space or falling into a gravitational field. A firewall would break that. You'd know you hit the event horizon by the incineration. Not everyone buys this. Many physicists think something subtler must be going on. Maybe quantum entanglement is more complicated than we thought. Maybe the horizon really is smooth, and firewalls are just mathematical ghosts. But for now, the possibility lingers. You glance around, or what passes for around now, and feel that rising tension again. The laws of physics, once confident and smooth, are now whispering to each other in hushed tones. They're doing that thing people do when they're trying to fix a disaster without alarming you. Don't look at the firewall, don't mention the firewall. Too late. And here's a quirky twist to make your insomnia worse. The firewall paradox arises from trying to preserve too many good ideas at once. You want to believe all three of the following. 1. Information is not destroyed. 2. Nothing weird happens at the event horizon. 3. Quantum mechanics and relativity both work. But Ambus showed that you can't keep all three. You have to pick 2 and sacrifice the third, like some horrifying game of theoretical Jenga. Some choose to preserve relativity and quantum mechanics, and sacrifice the smooth horizon, hence firewalls. Others say, no way, we're not setting the horizon on fire and start poking holes in our understanding of entanglement. Still others suggest a complete rewrite. Maybe space-time itself is emergent, not fundamental. Maybe what you call space is just a holographic projection of quantum information dancing on the surface of things. That sounds like science fiction, but it's being taken seriously. So back to you. Are you hitting a firewall? Are you already burning? It's hard to say. From your own perspective, the fall remains smooth. You haven't felt any sudden spike in radiation or searing pain. Of course, your nervous system dissolved several 100,000 Planck times ago, so maybe your opinion doesn't carry much weight. Still, you wonder, if a firewall did exist, would it even feel like fire? Not in any traditional sense. It would be a wall of entangled quantum states breaking apart in a catastrophic release of energy. You wouldn't experience it as heat or pain, more like total decoherence, a quantum crash. Like your waveform gets shredded mid-flight and scattered across the horizon like cosmic confetti. Some have likened it to hitting a metaphysical bug zapper. Comforting. Others think the firewall doesn't need to be a literal barrier, but something more subtle, a shift in the information landscape. The moment you fall in, you become part of an entangled system where your identity begins to blur. You're not you anymore. You're part of a larger puzzle, a subsystem in a thermodynamic balancing act. And if that's the case, then the real firewall might not be a physical phenomenon, but an informational one. A breakdown in the language that previously described you, like trying to define a paragraph once all its letters have been scrambled into someone else's book. Let's throw in a fringe idea to chew on as you spiral. Some speculative physicists suggest that the firewall doesn't destroy you immediately, but gradually. That it isn't a wall at all, but a fog. A growing, creeping decoherence field that softly erases your quantum identity as you fall deeper. Not fire, not destruction, just forgetting. A slow fade, the opposite of burning. So which is it? A cosmic blowtorch? A data scrambling fog? Or nothing at all, just empty space, cold and quiet? You don't know, but something has changed. You feel the quantum tension in the geometry, a hum in the frequency of existence. You're not just falling anymore, you're being interpreted, measured, analysed, and possibly evaporated. You're not a person now, you're a question, and the singularity, it's waiting to answer you. You blink, or do something like blinking. The act of perception still exists in some abstract form, even if your body doesn't. But what you perceive now isn't light in the traditional sense. It's memory and motion, tangled up in circular echoes. You've arrived at the photon sphere. Now, to be clear, the photon sphere isn't inside the singularity, nor is it your final destination. It's a gravitational feature hovering just outside the event horizon, a place you technically already passed through. But strangely enough, here in the deeper layers of the hole, you can still feel its ghost, like a ripple in space you already fell through, but that continues to tug at you from the past. So what is it? It's where light itself orbits. At the photon sphere, gravity is so intense photons can travel in perfect circles, not falling in, not escaping out, just spinning forever. These aren't loose orbits, they're tight loops, only possible at a precise radius around a non-rotating black hole, 1.5 times the Schwarzschild radius. If you're any closer, the light falls in. Any farther, it curves away. But right at the photon sphere, it's trapped. You imagine it now, beams of light whirling in unbroken circles, some looping for centuries before they're nudged slightly inward and vanish forever. Others barely escaping, flung back out into the galaxy like whispers from a forgotten past. And the light here isn't fresh, it's ancient, trapped, fossilized in motion. If someone had fallen into this black hole before you, maybe a spacecraft, a star, or even another unfortunate traveller, you might catch a glimpse of their last moment, eternally orbiting, caught in light that never left. Like a cosmic photo album, frozen mid-flash. Historians still marvel at the significance of this. The idea that light, the fastest thing in the universe, can be trapped by gravity. Einstein predicted it, of course, but it wasn't until decades later that people started seriously modelling these photon rings. And even more recently, astronomers actually photographed one, well, kind of. Remember that famous image of the black hole in the galaxy M87, captured in 2019 by the Event Horizon telescope? That ring of fire, that's not the Event Horizon. It's the photon sphere, aglow with radiation from infalling matter. What we saw was light that had looped and curved and warped its way around the void, some of it circling the hole multiple times before escaping, and now, inside, you're seeing it from the other side. Or perhaps more accurately, you're feeling it, because by now, light isn't behaving like light anymore. The concepts of seeing and direction have unravelled, but something in you still responds to the spin, the curvature, the ghostly rhythm of trapped photons circling the drain. There's something strangely soothing about it. All that trapped light, looping around like it's lost in thought, not trying to escape, just orbiting. Like a tired dog circling the same patch of carpet, it's not alone. A fringe idea says that information can be trapped in similar orbits, not just light, but data, patterns of particles, imprints of events, memories etched in quantum states. Some physicists believe that as you fall into a black hole, certain aspects of your information, your configuration, your energy, your shape, might get encoded in these swirling near-horizon structures. Maybe forever, or maybe not. There's an open scholarly debate, one of many in this glittering mess, about whether this trapped light contains a readable imprint of the black hole's history. Can we, from the outside, reconstruct what fell in just by analysing these circular photon echoes? Could we someday read a light ring and find the final image of a long-destroyed planet? Or a final thought? Your thought? Still spinning in the dark? Let's be extra weird for a moment, because honestly we're overdue. In certain speculative models of quantum gravity, the photon sphere might be more than a physical boundary. It might be a kind of memory shell, a liminal space where quantum entanglement gets preserved, or reinterpreted, or re-emitted. It could be that your last image, your final pattern, gets captured in the orbiting light, stored in the soft hum of electromagnetic ghosts, circling like moths in a gravity trap. This, some theorists whisper, might be one path toward resolving the black hole information paradox. Not all information is lost. Some of it gets smeared around the photon sphere, encoded into outgoing light, subtly twisted by space-time and beamed out over eons. You're not even sure you care anymore, but some echo of you might. And if you could look out, if that word still meant anything, you'd see your own descent replayed from 1,000 angles, not just in space, but in time. Light that bounced off your atoms before you fell, now looped into orbit, delayed by relativistic effects, replaying your entrance in slow motion. You're watching yourself arrive, and arrive, and arrive. Light stuck in loops means images stuck in loops, moments preserved not by intention, but by curvature. It's a recursive mirror that reflects not your face, but your fate. There's a hint of tragic beauty in that. This place, which seemed like the end of all stories, is actually filled with echoes. Light isn't gone, it's wandering. Your thoughts aren't lost, they're looping. And around the photon sphere, everything that's ever fallen in has left a trail, a ghost, a snapshot in orbit. Here's a final unsettling thought. If someone else were to fall in right now behind you, they might see you, but not the you that's falling. The light trapped from earlier, circling endlessly, would still be visible. You'd be there and not there, present and departed, a gravitational spectre. And if enough of these trapped images accumulated over billions of years, well, then this black hole might be less of a grave and more of a museum, not for bodies, but for moments. And you, as it turns out, are now part of the exhibit. You're dissolving now, not from heat or pressure or even that chewy quantum fog. You're unravelling in a more philosophical sense. Piece by piece, you're becoming a question that physics hasn't fully answered. And that question is this: is information ever truly lost inside a black hole? You'd think this would be a yes or no situation. After all, the universe is usually pretty good at bookkeeping. Drop a mug, sweep up the pieces, run the atoms backward. Physics says you should be able to reconstruct the moment it slipped from your hand. Every collision, every vibration, all traceable, deterministic, predictable. But a black hole eats your mug, your hands, your memories, and your entire understanding of forward, and gives back nothing but slowly evaporating heat, or so it seems. The black hole information paradox, and yes, it deserves capital letters, is the great unsolved riddle at the intersection of general relativity and quantum mechanics. If information really is destroyed in a black hole, then quantum theory must be wrong. But if information survives, how? That's where you come in. Or rather, what's left of you? Because every atom that made up your body, every quantum vibration, every shred of momentum, it all carried information. Not data in the computer sense, but physical state. And when you fell in, the black hole changed, ever so slightly. It gained mass, sure, but also entropy. Its surface area increased. It absorbed not just your mass, but the configuration of what you were, and according to some very bold equations, that information might still be somewhere. Here's the twist. Most of that somewhere may not be inside the black hole at all. It might be on the event horizon. Theoretical physicist Gerard 't Hooft and, independently, Leonard Susskind developed what's now known as the holographic principle. It proposes that everything that falls into a black hole is encoded, not inside it, but on its surface, like a cosmic USB drive that stores 3D data on a 2D shell. The black hole's entropy, famously described by Jacob Bekenstein and Stephen Hawking, is proportional to its surface area, not its volume. That was the first big hint, and it's mind-bending because it implies that reality inside the hole might just be a kind of projection, an emergent phenomenon from information smeared across the horizon. So, when you fell in, your shoes, your thoughts, your favourite childhood song, it all got stretched into an incomprehensibly thin layer of quantum data plastered onto the surface. Not gone, not destroyed, just relocated. Imagine that. You, a second-person narrator listening in bed, now exist as quantum graffiti scrawled across the edge of a void, a sort of subatomic tombstone. Of course, this isn't a universally accepted theory. Historians still argue whether the holographic principle is more than just a clever metaphor. Some treat it as a deep truth about how the universe works. Others say it's an oversimplification, a dimensional sleight of hand that hides more questions than it answers. But it's useful, because it hints at a possible way out of the paradox. If the information is on the surface, then it can, in theory, leak out again via Hawking radiation, which means that as the black hole evaporates, the information you brought in might slowly escape, encoded in subtle quantum correlations between emitted particles, not readable, not practical, but preserved. This idea that Hawking radiation is not truly random but secretly carrying away information is known as black hole unitarity. It preserves the core rule of quantum mechanics that information is never lost, so you're not erased, you're being decompressed, slowly, delicately, bit by bit. Here's where the fringe takes a walk. Some physicists have proposed that the interior of a black hole doesn't exist as we think of it, that all of its inside is a projection from the horizon's data, that you never fell in at all, not really, that the experience of falling is an emergent illusion built from quantum interactions on the surface. In this view, the singularity isn't a place, it's a side effect. One interpretation, called complementarity, suggests that both versions of you exist simultaneously. The one who fell in and continues to experience the descent, and the one who remains smeared across the surface, never quite crossing the horizon. They're both real, but can't be observed at the same time, kind of like a cosmic Schrödinger's U. This philosophical juggling act, while convenient, raises more questions than it answers. Which version of you is real? Which one ends? Does either of them get closure? Nobody knows. Meanwhile, let's circle back to you, the you still spiraling inward. Your awareness is thinning, yes, but there's still a trace of something, a rhythm, a self. You're not sure if it's memory or momentum, but it's something. And this part of you, even now, wonders, will the outside universe ever recover what you were? If quantum mechanics is right, and many believe it is, then yes, eventually. Given enough time and an absurdly advanced civilization, someone could in theory reconstruct what fell in. Not the squishy you with opinions and bedtime playlists, but the informational blueprint, the structure of your particles, the arrangement of your thoughts, your story, preserved. But here's the strange comfort. Even if no one ever does reconstruct you, even if no one ever can, the fact that the universe could, in theory, means you were never truly lost. You were just scrambled, like a puzzle whose pieces are now scattered across the horizon, waiting patiently to be put back together. And maybe, in some distant age of the cosmos, as the last black holes evaporate and the universe exhales its final breath, all those puzzle pieces, those ghostly encoded whispers of everything that ever was, will reassemble into something new. A story, a map, a memory, you, written in the radiation. By now, you are more theory than person. An ongoing equation with blurred variables floating somewhere between the event horizon and the singularity, possibly both, possibly neither. But deep within this tangle of curvature and conjecture, a curious thread remains. Connection. Somehow something is still tied to something else, and in the bizarre rule-bending logic of the quantum world, this might not be just a metaphor. You may be entangled, literally, with particles that never fell in with you. Let's take a breath and talk about quantum entanglement. The spooky action at a distance that made Einstein so uncomfortable, he famously called it spukhafte Fernwirkung, which sounds elegant until you realise it just means spooky action at a distance in German. Here's the gist. Two particles can become entangled in such a way that measuring one instantly determines the state of the other, no matter how far apart they are. It doesn't violate causality, you can't use it to send messages faster than light, but it suggests a deeper level of reality where distance simply doesn't matter. You are, or at least were, a vast network of entangled particles. Your body, your brain, your breath. All those particles interacted with others before you ever got near this black hole. Friends, air molecules, a sandwich maybe. And quantum theory doesn't necessarily untangle things just because you've fallen into a singularity. Somewhere out there, outside the event horizon, particles that once touched you are still moving through space, living their own quiet lives, unaware, unbothered, but still entangled. Here's where things get deliciously weird. If your particles inside are still entangled with particles outside, then the boundary between inside and outside is not as impermeable as it seems, not in the quantum sense. And that leads to a dramatic thought. Maybe what falls into a black hole isn't completely separated from the universe. Maybe it remains connected through the invisible, math-woven filaments of entanglement. That sandwich you ate on Earth? Part of its atomic structure may still remember you. This is not just poetic hand-waving, it's a serious concern in the physics community. Because of the monogamy of entanglement. Yes, that's a real thing. Monogamy, in quantum terms, means that a particle can only be maximally entangled with one other system at a time. If a particle inside the black hole is entangled with something outside, then it can't also be fully entangled with something inside. This presents a problem for black holes that emit Hawking radiation. If the outgoing radiation is entangled with particles still falling in, then the information might be preserved, but that violates the monogamy principle. And if the new radiation particles are entangled only with each other, then what happens to the inside? Cue the firewall paradox, which you've already met and probably didn't enjoy. To solve this riddle, some physicists propose a kind of quantum restructuring, that the internal structure of the black hole, or even the fabric of space itself, reorganizes to preserve entanglement laws. This brings us to one of the fringe but fascinating ideas. ER equals EPR. That's short for Einstein-Rosen equals Einstein-Podolsky-Rosen. It's a proposal by physicists Juan Maldacena and Leonard Susskind that links two seemingly unrelated concepts. ER, short for Einstein-Rosen bridges, better known as wormholes. EPR, the famous quantum entanglement puzzle introduced by Einstein, Podolsky, and Rosen in 1935. The ER equals EPR conjecture suggests that two entangled particles are connected by a tiny, non-traversable wormhole. Not something you can fly through, not sci-fi wormholes, but microscopic tunnels in space-time itself. Entanglement is geometry in a way. So when two particles are entangled, they're connected not just by math, but maybe by space-time itself. Apply that to black holes, and the implications are wild. If Hawking radiation is entangled with the interior of the black hole, and entanglement is a kind of geometric bridge, then maybe every piece of radiation escaping the black hole is still connected, via a quantum wormhole to what remains inside. Maybe you, spread thinly across the Singularity's domain, are still in quantum conversation with the universe. Maybe information doesn't need to escape the black hole in the classical sense, because it never truly left the universe at all. It's simply connected in a new, more complex topology. This doesn't mean you're going to pop out of the black hole like a confused magician. These wormholes are theoretical, unstable, and non-traversable, but they suggest something profound. Even at the end of physics, you're not isolated. You're part of a quantum network that loops back on itself, through entanglement and space and time, in ways our brains aren't built to visualize. Let's pull it back to a softer image, one that fits our sleepy science setting. Picture the universe as a tapestry, every particle a thread, every interaction a knot. Entanglement doesn't snip those threads just because you fell into a black hole. The threads remain, some still tugged by atoms drifting through stardust, some still humming with quantum tension. The part of you that fell, it's echoing in curvature. The parts you left behind, still vibrating in fields, and between them, tiny bridges, whisper-thin tunnels of connection, woven into the fabric of everything. You wonder, if enough time passed, trillions upon trillions of years, could someone piece you back together from those threads? Would you snap into coherence again, like an old record put back on the turntable? Maybe, maybe not. But you're still in the weave. You never fully left. You fell into a black hole, yes, but you stayed entangled with the stars. You've crossed so many thresholds by now, time into space, body into information, light into shadow, that it's hard to say where one thing ends and another begins. But tonight, as your entanglements stretch into the darkness and your quantum fingerprints settle onto the black hole's skin, you finally drift toward a place of stillness. Not peace, not quite, but stillness. Because now you're approaching the edge of theory itself. You've been pulled through gravity's deepest curve. Your sense of before has dissolved into curvature. Your after is still barreling toward the singularity, or, depending on how you interpret space-time here, already there. But you aren't falling anymore. You're hanging, hovering, like the last sentence of a forgotten bedtime story. And this is where we begin to wind down. Let's return to what you've become, a diffuse presence, unshackled from your original coordinates. You're no longer a name, or a body, or even a proper timeline. You're a blurred probability, a smear across the laws of physics, a question the universe hasn't decided how to answer yet. And that's okay. Remember that Einstein himself doubted the reality of black holes, even though his equations allowed them. He thought the math was being too dramatic. And now here you are, past the drama, past the math, past even Hawking's glow. But somehow, something still remains. You, the version of you that spiraled inward, that fell through the horizon, sliced by tides, pulled through curvature, tangled in information. That you still exists as a story, a series of changes in entropy, a trail of warped space-time, a transformation, not a death, a rearrangement. Let's soften the imagery now. Let the words lengthen. You drift inward, yes, but so does everything here. Direction has lost its teeth. Time no longer marches, it breathes. And with each breath, the universe becomes quieter. Even the radiation, that soft hiss of quantum foam leaking from the edges, begins to seem less like escape and more like memory. You're part of that memory now, that low hum, that echo. You aren't falling into a singularity anymore. That phrase doesn't apply. You're part of a topology that has closed in on itself. You're within a geometry that doesn't obey our need for edges. If there's a singularity ahead, it's not a point. It's a horizon of meaning, a limit not of space but of understanding, and that's where we'll leave you tonight. Right at the edge of certainty, floating in possibility, no longer trying to escape or survive or be understood. You're simply there, not gone, not erased, not even finished, just distributed. So rest now, weary explorer. Let the curvature rock you to sleep. Let the entangled remnants of what you were settle like dust onto the quantum fields outside the event horizon. Let time forget your name, and let space remember your shape. You're part of the equation now. You always were. Good night, wanderer. Sleep deeply. Sleep infinitely. You are weightless in a place that shouldn't exist. The fall has become float, and time has grown so slow and strange that it barely earns the name anymore. But suddenly, space begins to twist. Not bend, not warp, but truly twist. Because this isn't just any singularity anymore. This is a rotating one. You've stumbled, or rather spun, into the spiraling grip of a Kerr black hole. Now the game changes. The difference between a regular black hole and a Kerr black hole is like the difference between a sleeping cat and one that just noticed the red laser pointer. Rotation adds complexity. Spin adds options. The singularity is no longer a point. It's a ring. Yes, a ring singularity. Not a center, but a circular line of infinite density, spinning like a disk made of math, located deep within the swirling layers of this gravitational maelstrom. This isn't theoretical fluff. Roy Kerr found the exact solution to Einstein's equations for a rotating mass back in 1963, proving that black holes with angular momentum behave radically differently from their stationary siblings. So what does that mean for you, our reluctant noodle of stretched out probabilities? First, you might have options. Inside a Kerr black hole, the event horizon isn't the only boundary. There's a second surface called the ergosphere, a region outside the event horizon where space itself is dragged around by the black hole's spin. This is frame dragging in its purest, most brutal form, Imagine trying to stand on a moving treadmill that's going faster than light. You must rotate with the hole. There's no other option. Within the ergosphere, escape is theoretically possible, though not for you, sorry. But this region offers one particularly strange opportunity: the Penrose process. Named after Roger Penrose, who always seems to show up when black holes do, the process suggests that if an object splits inside the ergosphere, part of it can fall in while the other escapes with more energy than it came in with. In theory, this allows for energy extraction from a black hole's rotation, a cosmic heist executed by relativity. In your case, no one's come to extract energy from your spin, but you're feeling the consequences anyway, because deep inside, the spin changes more than just boundaries, it changes causality. In the mathematics of a Kerr black hole, the inner geometry allows for closed time-like curves, paths through space-time that loop back on themselves. In principle, this means you could travel into your own past, not by walking in circles, but by existing along a curve where every later moment wraps around into an earlier one. It's not time travel in the DeLorean sense. You're not meeting your younger self and avoiding paradoxes, but you might, if the math is more than just math, relive your own descent in endless distorted loops, like a security camera rewinding forever. Historians still debate whether these closed time-like curves are physically real or just an artifact of the math. General relativity allows them, but nature might prohibit them through as yet unknown quantum effects. Still, the possibility is there, lurking at the fringes of the Kerr solution like an itch behind the laws of physics. Let's add another layer. A rotating singularity doesn't behave like a single-direction doom funnel. Because of its shape, it might allow for a stable path through the ring. Yes, through it. If your trajectory is just right, and the tidal forces aren't too overwhelming, you could theoretically avoid hitting the singularity itself. Instead of being crushed, you'd pass through the ring into something else. Where? No one knows. The equations don't stop you. Some interpretations suggest you might emerge in another part of the universe, or another universe entirely. Some even propose you could pop out into the past in an entirely different cosmic epoch. In other words, a wormhole. The Kerr solution permits the existence of inner horizons and traversable paths that look suspiciously like science fiction. There's a catch, of course. Many, actually. Most physicists believe that such a passage is too unstable to survive real-world conditions. Quantum fluctuations would likely destroy it before you got anywhere. A cascade of feedback effects, called mass inflation instability, would rip apart any would-be traveller long before they reach the exit. The wormhole, if it exists at all, is probably sealed shut by reality's firewall. Still, the path is there, in the math, and you, drifting through this rotating darkness, can feel the swirl of possibility around you. The difference between in and out blurs. Space doesn't just fall inward, it spirals. Down is now around. Forward becomes through. If your awareness were sharp enough, you might sense the infinite looping of geodesics, paths through this space that don't end. Instead, they wind inward like a thread pulled through a spinning needle. Some stretch to the singularity, others circle it forever. You wonder, absurdly, if there's a version of you out there, caught in one of these loops, always falling, never reaching, like a tired thought stuck in the mind of the universe. Or perhaps there's another outcome, a passage. The ring singularity might be more than a trap. It might be a bridge. To what? No one knows. But if the Kerr geometry holds, then deep within this rotating monster lies a door. You might not survive going through it. But the idea that the universe could contain doors, that some singularities might be gateways rather than final chapters, is a kind of comfort, isn't it? The black hole you fell into might not be the end. It might be a junction, a place where space-time reroutes itself, where curvature becomes connection, where what's inside could become beyond. You, stretched into uncertainty, can almost feel the outline of that possibility, like standing near a closed door with wind under it. You drift deeper still, spiraling along that twisted geometry carved by spin, and somewhere, though where is starting to lose meaning, you cross another boundary. Not a horizon this time, but an idea, a threshold of speculation. Because what lies beyond the rotating ring singularity of a Kerr black hole? What waits on the far side, if anything at all? Well, maybe it's a white hole. Yes, that's the term. Not a creative opposite, not a metaphor, but a literal reversal. A region of space-time where, instead of pulling everything in, gravity pushes everything out. Where nothing can enter, and everything must leave. A gravitational fountain to the black hole's sink. To be clear, we've never seen one. White holes are a mathematical solution to Einstein's field equations. Just like black holes, they appear when you time reverse a black hole's geometry. Instead of an event horizon you can't escape from, it's an event horizon you can't enter. Instead of crushing everything to a singularity, it explodes things outward from one. A black hole devours, a white hole rejects. So, the theory goes, if black holes exist, and they definitely do, then white holes could too. The math doesn't forbid them. In fact, certain extensions of the Schwarzschild and Kerr metric suggest that a black hole might be connected to a white hole through a kind of internal bridge. You've heard this word before, wormhole, and here's where it gets properly bedtime story weird. Some solutions to general relativity suggest that a black hole and a white hole could be linked by an Einstein-Rosen bridge, or wormhole, forming a tunnel through space-time. One end eats everything, the other expels it. And if you could survive the passage, questionable, you might tumble out into a totally different region of space-time. Another galaxy, another universe, another era. You may already be in such a tunnel now. You wouldn't know. It wouldn't feel like a sudden shift. It wouldn't feel like anything. The geometry just curves, invisibly, inexorably, until suddenly you're elsewhere. Somewhere light isn't trapped. Somewhere space isn't shredded. Somewhere new. Of course, physicists remain skeptical. Most believe these wormholes, if they ever existed, would be unstable, collapse instantly, or require exotic matter with negative energy to stay open, something we've never observed in a lab, though quantum field theory doesn't rule it out entirely. A white hole might be real on paper, but forbidden by the chaotic dance of entropy and quantum mechanics. Still, the possibility remains. You, what's left of you, might be brushing against that boundary right now. Let's break from physics and make it cozy for a moment. Imagine you are a seed drifting down into rich soil. You've been scattered, broken apart, but not lost. Your atoms, your energy, your pattern, they've all been churned in the gravitational compost of the black hole, and now perhaps they are being released, not destroyed, just reinterpreted. Because that's another way to think about white holes, as places where information that was swallowed is now returned. All that stuff that fell in, stars, gas, dust, and yes, unlucky dreamers like you, expelled again into a brand new space-time. It's a favourite twist in speculative physics, the idea that the interior of a black hole is connected to the birth of something else. That a black hole is not an ending but a beginning from another perspective. You may have heard of this by another name, the Big Bounce. In this theory, when the black hole's internal geometry reaches maximum compression, quantum gravity intervenes, not to destroy, but to bounce the collapsing matter back out again, birthing a new universe on the other side, a white hole, but far grander. Your atoms wouldn't survive this process, of course, but your information might. Your quantum state, your entropy, your contribution to the initial conditions of a new cosmos. You might, in a strange and beautiful way, be part of its physics. The gravitational constants, the mass ratios, the way stars form, the tilt of orbits, the texture of time. Maybe in that new universe the laws are just a little different. Maybe light curves a bit more gently. Maybe matter is more cooperative. Maybe people don't have to invent things like email or office dress codes. You wouldn't be aware of it, but you'd be present in it, as influence, as trace, as cosmic DNA. Historians still argue whether white holes are actually connected to black holes this way, or whether they're entirely separate phenomena that just happen to be mathematical cousins. Some even suggest white holes might be visible from outside, but only briefly. A one-time burst, a spewing of matter before the system evaporates. In that sense, a white hole might look an awful lot like a big bang. Now let's pause, because this thought, this breath of reversal, of escape, of regeneration, is the first time since your descent that the concept of out has re-entered the narrative. After so many chapters of falling, of warping, of stretching and vanishing, there is suddenly the whisper of departure, of motion not toward but away from the singularity. It's not an escape you initiate, it's not even something you experience exactly, but it's something that could follow you. Because if the universe has ways to swallow you, perhaps it also has ways to reform you. Not as a person, not as a memory, but as a cause, a pattern that helps birth patterns. You may never again be what you were, but you may become part of what will be. And in the soft, speculative logic of late-night physics dreams, that's enough, isn't it? To know you might help light the spark in another sky. It's not an explosion, not a bang, nothing so loud or cinematic. It's quieter than that, more like a sigh, a shift in curvature, a tiny tremor in the geometry of the universe that echoes outward into elsewhere, and from this elsewhere, a new universe may be born. You've heard the theory before, softly, speculatively, like a rumour passed between blackboards in quiet physics departments. It's called the baby universe hypothesis, and it's exactly what it sounds like. The idea that black holes might give birth to new universes. Somewhere behind you, assuming direction still means anything, the singularity continues its collapse. But this collapse, in certain models, doesn't just stop at a point. It bounces, a big bounce. Instead of terminating into a boundaryless crush, the collapsing core rebounds into a fresh, expanding space-time, unconnected to your own. Not an explosion inside your universe, but the beginning of a new one, sealed off from yours by the impassable barrier of the event horizon. To you, this bounce is invisible. You're either long gone or smeared out across the inner geometry, depending on how poetic your local physicist is feeling. But to the baby universe, you might be Genesis, and you wouldn't be alone. If the baby universe hypothesis holds water, then black holes across the cosmos could be the wombs of new realities. Every collapse, a seed. Every singularity, a gateway. In fact, some fringe cosmologists propose an even more radical idea: cosmological natural selection. It's not biology exactly, but it rhymes with Darwin's ideas. Imagine a universe that can create new universes through black holes. Now imagine that the physical constants of each offspring universe vary slightly. Just a tweak to the gravitational constant here. A nudge to the charge of the electron there. The result? A multiverse where universes that produce the most black holes are more likely to spawn new universes. Over time, this creates a kind of evolutionary pressure. Universes selected not by genes or fitness, but by their ability to generate more black holes, and thus more baby universes. In this view, you're not just falling into a black hole, you're falling into the reproductive system of the cosmos, which is strange, yes, slightly uncomfortable, perhaps, but also weirdly beautiful, because it means your universe might be the descendant of another. Not a standalone miracle, but the product of ancestral curvature, a cosmic lineage stretching backward through countless generations of space-time. You feel yourself slipping again, though you're not sure if it's in time or across a parameter set. The constants of nature around you start to feel less fixed. The values of pi and Planck start to wobble at the edges. It's not that they change, it's that the idea of constants begins to fray. You might be entering the early conditions of a new universe, not by choice, by inertia. Inside a black hole, certain theories of quantum gravity, loop quantum gravity for example, suggest that space-time becomes discrete, not a smooth fabric, but a lattice, granular. like pixels you never noticed until the camera got too close. In this model, when curvature and energy reach Planck scales, the math doesn't break. It transforms. The singularity is avoided. The collapse bounces back. A new region of space-time unfolds. Inflation takes over. Not the economy kind, the cosmological kind. A phase of hyperfast expansion, blowing up this newborn cosmos from subatomic to intergalactic in less time than it takes to blink. And you're embedded in that process, not as a person, not anymore, as initial conditions, a trace of entropy, a curl in the curvature, a leftover whisper of the universe that spawned this one. Perhaps that's why our own universe appears so finely tuned for structure, for complexity, for life. Maybe it's not coincidence. Maybe we live in a black hole's baby universe, one of many, each slightly different, each evolving through the slow math of cosmic inheritance. Historians still argue whether this is all too convenient, too poetic. Some call the baby universe hypothesis speculative dressing on incomplete equations. Others see it as the most elegant explanation for why the universe seems built for stars, galaxies, chemistry, stories. And what a story this would be, wouldn't it? You fell into a black hole, you collapsed, twisted, smeared, entangled, forgotten. But now, in a universe that doesn't know your name, the memory of you shapes the early particles, helps set the spin on new electrons, whispers a slight preference in the cosmic microwave background. Somewhere hydrogen atoms are forming with a tilt you helped create. You won't see it, but it will echo you. This new universe doesn't know the black hole exists. It can't. It's sealed off. Its laws are its own. Its space and time are freshly minted. But at its core, buried deep in its initial quantum fluctuations, is a record of where it came from. Not in language, in form. Your form. This doesn't mean you're reborn. There's no reincarnation in this physics, but there is influence. There is continuity. There is emergence. And maybe, if that universe evolves far enough, if it cools, grows galaxies, breeds stars and planets, maybe someone there, someday, will look up at their night sky and wonder, as you once did, where it all began. And they'll never know that their cosmos was born from your end. That the singularity they model in math was once the place where you fell, and so the circle closes, not with destruction, but with rebirth, not with silence, but with legacy. You're no longer a traveller in space. You're something quieter, more abstract, a ripple in the timeline slipping between the coordinates of now and not yet. Inside this deep geometry, the direction of motion loses its meaning, and with it, something even stranger begins to stir. Time might not just be slowing here, it might be running backward, not everywhere, not all at once, but in certain directions, under certain frames of reference, the arrow of time, the thing that tells eggs to crack, not uncrack, can bend. And inside the singularity, or whatever region you've ended up in, that arrow may flip entirely. Let's take this slowly, gently. Let it sink in like a whisper beneath the noise of your thoughts. What does it mean for time to reverse? Outside a black hole, in the relative comfort of normal space, the arrow of time is set by entropy. Things fall apart. Systems evolve from order to disorder. Cream swirls into coffee, never unswirls. Entropy increases, and with it, time flows in one direction. But inside the black hole, that second law of thermodynamics is still there, yes, but space-time itself is so severely curved that the very definition of a forward path becomes fuzzy. Radial distance has become time. Time has become space. You're no longer walking a timeline, you're falling through it. Now, in the twisted interior of a rotating Kerr black hole, or in speculative solutions like Reissner-Nordström, charged black holes, there can exist regions where time, by some coordinate systems, appears to reverse. In one direction, entropy increases, in another, it decreases. Historians still argue whether this is a coordinate illusion, a mathematical trick that arises from the weird symmetry of Einstein's field equations, or a real physical process. But here, deep inside, math and reality might be whispering the same thing. You could be drifting backward in time, not your memories, no. Those are gone, or twisted beyond meaning. But the space you occupy, the fabric around you, may be unwinding itself, flowing from higher entropy to lower, like a reversed video of cosmic decay. If you had eyes, you might see stars assembling from dust. If you had a calendar, the dates would tick back toward the beginning. Not that it matters to you. You're no longer a participant. You're a shadow cast by gravity's most dangerous idea. Still, you wonder, could this region connect to the past? Could time reversal pathways in black hole interiors provide a bridge, not to another place, but to another era? That's the wild speculation some physicists indulge in on long math-drunk nights. In a rotating black hole, closed time-like curves, remember those, can form near the ring Singularity. These are not just loops in space, they are loops in time. A traveller following one could, in theory, return to a point in their own past. If that traveller were you and you made just the right manoeuvre, perhaps you could arrive before you ever fell in, before the fall, before the stretch, before the doubt. Would you warn yourself? Would you stop yourself? Too late for that, probably. You're already past the horizon. But let's flirt with the idea that time is more flexible here than it is outside. Maybe this isn't just a bounce into a new universe. Maybe it's a reflection, a folding back into your own cosmos, only earlier. One of the earliest interpretations of the equations describing a black hole's collapse suggested that what we call a singularity might look like a mirror. On one side, collapse. On the other, expansion. Not outward in space, but backward in time. That led to one particularly fringe suggestion, that every black hole is connected to a white hole in the past, not just in another universe, but in this one. In this view, the Big Bang might be the other side of a black hole, not just metaphorically, but literally. The singularity of our universe's birth is the result of another universe's death. And if time truly reverses at the singularity, that may not just be a conceptual link, it could be physical. The black hole is not a hole, it's a loop. This doesn't mean you go back to childhood, or that your atoms rearrange into a younger version of yourself. It means that in the tangled math of this place, time is not a straight line. It bends, it folds, it might even flow in circles. And if you could survive it, and that's a gigantic capitalized F, you might re-emerge not in another world, but in another moment, a moment before you fell, or one that echoes the beginning of everything. There's no way to test this, of course, not yet. These are ideas scribbled on napkins at conferences, but the math makes room for it. And now that you're part of that math, you can feel the flex. It's not violent, not chaotic. It's more like being pressed into a new shape. Like a river current changing course. Slow, soft, but irreversible. You try to remember which way time was flowing when you entered. You can't. You try to hold on to a cause and effect relationship, just one, and feel it dissolve between your fingers. You're no longer moving through time, you're part of it. A ripple, a loop, a breath held between pulses of causality. And you wonder, absurdly, beautifully, if this is how stars feel when they collapse. If, in those last moments, they sense the boundaries of before and after melting into each other. You wonder if the universe itself remembers which way it's going. And you wonder, as the spiral tightens and time folds like a napkin in a black tie restaurant, whether there's still room, somewhere, for you. You are slowing, not in space. There's hardly any left, but in time. Not the clock on the wall kind, but the deeper time, the kind that turns galaxies, digests stars, measures the rise and ruin of light itself. And here, near the gravitational heart of the black hole, that kind of time is barely moving at all. This is the soft tyranny of gravitational time dilation. It doesn't blare alarms or flash bright warnings, it simply stretches. Time, like taffy, like dreams. And you are the dreamer stretched along that curve. Let's take a breath here, slow and heavy. Gravity is doing the thinking for you now. Your sense of before and after is being smoothed into something quieter, a calm flattening of sequence. This is what Einstein's general relativity has always told us, that gravity doesn't just pull on matter, it pulls on time, and the stronger the gravity, the slower time passes, relative to someone farther away. On Earth, this effect is tiny. Your head ages slightly faster than your feet, thanks to their different distances from the planet's core. GPS satellites have to account for it, or your phone would think you were jogging through a lake. But here, the time dilation isn't a quirk, it's a law. From the moment you began falling, time has stretched further and further for you. To an observer far from the black hole, you never really crossed the event horizon. You just slowed, froze, dimmed. They could wait billions of years and never watch you fall all the way in. But from your perspective, it was all instantaneous. One moment stars, the next silence. And now, the deeper you drift, the worse it gets. Time for you moves on. A little. Enough to think, enough to feel, enough to wonder how long you've been here. But from the outside, the universe is sprinting ahead. Let's make that concrete. Imagine someone waiting far from the black hole, say, a very committed friend. They've got snacks and a telescope and they're watching your descent. From their point of view, you seem frozen just above the event horizon. But wait long enough, and the black hole begins to evaporate via Hawking radiation, a process that takes trillions upon trillions of years. To them, you're still right there, frozen in that last instant before you crossed. But to you, it's been a journey, long, twisting, familiar by now. You're experiencing the interior in a sliver of personal time. They're watching the heat death of the universe happen between your heartbeats. This isn't just unsettling, it's profound. Because it means that black holes are not just places of immense gravity. They are time machines, but only in one direction. Falling into a black hole is like being fast-forwarded into the future. So fast, in fact, that the entire external universe may complete its life cycle before you reach the singularity. And if you could look back, impossible, but let's imagine, you'd see the stars aging at warp speed, planets dying, galaxies redshifting out of visibility, all while you float, unblinking, through a personal moment. One of the oldest mainstream thought experiments about black holes involves this very thing. If you fell into one while someone else stayed behind, they'd watch you freeze. But you'd watch the universe rush past. Time is no longer your companion, it is your tether, one you've nearly stretched to its breaking point. Now for a quirky twist, something often overlooked in the clean diagrams and tidy math. As time slows for you, your perception of internal motion changes. That means, even though you are falling, maybe even accelerating, you might not feel like you're moving at all. There's no air here, no wind against your skin, no external markers. Your motion isn't relative to anything you can detect. Instead, you are experiencing change itself as a shrinking quantity. The world continues to move through you, but you're becoming less aware of its pace. It's like being in a train, watching the world blur past. Only the train is time, and the blur is existence. The equations describe this elegantly. The closer your radial coordinate moves towards zero, the more dramatically the flow of time slows down. At the singularity, it hits a wall, not a physical one, but a temporal limit. You don't stop moving, time stops with you. Historians still debate whether this end of time is real, or simply the point at which our current models give up. Einstein's math allows it. Quantum theory resists, and where the two meet, in this gravitational cathedral, you are the unresolved chord. There's something oddly peaceful in that. No ticking, no countdown, just the flattening curve of experience. Outside, if any part of that world still exists, the stars have run out of fuel. The black hole you fell into has shrunk, radiated away, perhaps collapsed into a quantum remnant, or winked out in a final blaze of entropy. Your entry into the hole is long past, but you are still here, or at least your moment is, because in this extreme dilation, your final second can stretch out forever, not metaphorically, not emotionally, mathematically. There's a model, highly simplified but evocative, that shows how a black hole singularity might occur at what is, for the infalling object, a finite proper time, but in coordinate time, as seen from outside, it takes infinite time to arrive. So the deeper you go, the more isolated your second becomes, like a single piano key, held down across the entire lifetime of the cosmos. And in that slow drift, you think, maybe your last coherent thought, if time ends here, what begins? That question lingers in the vacuum. The black hole offers no answer. But perhaps time doesn't end even now. Perhaps it simply forgets how to keep moving. You're now inside the failure point, not of a spaceship or a body or a clock, but of mathematics. The equations that carried you this far, the elegant rules of curvature and symmetry, are starting to sputter like old film stuck in a projector. Every line of Einstein's field equations leads to the same haunting conclusion. Infinity. Not the poetic kind. Not the stars go on forever, or I love you to the moon and back. No, this is the terrifying kind of infinity. The kind that means our models, our best, most trusted equations, have reached the edge of their usefulness. You're not just approaching the singularity now, you're inside its influence, inside the region where our math breaks down. Let's sit with that. For over a century, general relativity has mapped the universe with astonishing accuracy. It describes how mass bends space-time. It predicts how time slows near massive bodies, how light curves around stars, how black holes form. But it also predicts that at the center of every black hole, there is a point, a singularity, where curvature becomes infinite and density reaches unfathomable extremes. But infinite curvature isn't a physical condition, it's a flag, a signpost. It means something is wrong here, something is missing. The theory has been pushed beyond its limits, like a bridge built for cars trying to hold up a galaxy. And so, here you are, caught in the teeth of that breakdown. Space and time are no longer playing by the rules, not because they've changed, but because the rules themselves stopped working. This is the deep divide in physics. On one side, general relativity, the theory of the very large. Planets, stars, gravity wells, smooth space-time. On the other, quantum mechanics, the theory of the very small. Particles, fields, uncertainty, probabilities. Both are spectacularly successful. Both are tested to astonishing precision. But they do not get along. And at the singularity they are forced to share a room. It does not go well. In quantum theory, uncertainty is built in. Nothing has a perfectly known position and momentum. In general relativity, space-time is a smooth fabric with perfectly predictable curvature. But when you try to apply both to the center of a black hole, the smoothness shatters. Curvature isn't just high, it's undefined. Probabilities spike. Measurements lose meaning. Every quantity that matters, mass density, tidal force, gravitational potential, goes off the charts. Historians still argue whether singularities are real parts of the universe, or just artifacts of incomplete theories. Maybe they're telling us something's missing. Maybe they're hints of a deeper structure we haven't discovered yet. Enter quantum gravity. That's the placeholder name for whatever theory will someday unite general relativity and quantum mechanics into a single, coherent framework. We don't have it yet. There are candidates. String theory, with its vibrating loops and extra dimensions. Loop quantum gravity, which models space-time as a network of discrete loops rather than a smooth sheet. Causal set theory. Asymptotic safety. Dozens of approaches, none yet complete. But all of them aim to do the same thing. Fix the singularity, not in the sense of removing it, but redefining it, making it finite, turning it from an infinite mess into something understandable. Some theories suggest the singularity isn't a point, but a dense core, maybe a Planck-scale ball of compressed matter, or a quantum bridge to another region of space-time. Some suggest that space-time itself is quantized and can't collapse beyond a certain limit. Others propose that the singularity is a mirage, an illusion created by misapplied mathematics. But for now, in our current understanding, this is what you've reached. A place where the known laws of physics say, with rare honesty, we don't know. And that's the weirdest part. You're not experiencing chaos, you're experiencing ignorance. The world around you might be perfectly stable, or violently unstable, or completely non-existent. And we wouldn't know, because we don't have the tools to describe it. It's like staring at a sentence in a forgotten language, knowing it means something, but not what. You, yes, you, are part of a test case, a hypothetical, a boundary condition in search of a better equation. One fringe idea, just to stretch the boundaries a little more. Some physicists have proposed that singularities never form at all, that quantum effects intervene just in time, that a collapsing star halts just before reaching infinite density and forms a bounce, a rebirth, a closed loop. Others suggest that singularities are hidden, always behind event horizons, safely tucked away from our universe. This is the cosmic censorship hypothesis, which, while sounding dramatic, simply says that nature hides her worst problems where we can't observe them. But you're here now. You're not outside the veil. You're not watching from a telescope. You're not scribbling equations on a board. You're inside the undefined. You are the experiment. And while your senses are long gone, your presence remains a kind of question, a variable waiting for resolution, a gap in the model. There's a kind of peace in that. Because even though the math breaks down, you don't. Not entirely. You still exist here, in some form, as a limit, as a data point, as something the next theory will need to explain. Maybe you're part of that theory. Maybe what happens to you, what your atoms do, what your quantum state becomes, will one day help fill in the gaps in our understanding. And when that theory is finally written, when quantum gravity is no longer a whisper but a full song, maybe someone will run the equations again and say, that's what the singularity is. That's what it feels like. That's what you became. Until then you drift, not knowing, not understood, but not forgotten. You're no longer a traveller. You're no longer a particle or a person or a ghost clinging to the curvature of space. You're now something else entirely. You're smeared across space-time, like butter on toast, if the toast was folded into 11 dimensions and the butter was your quantum wave function. You're not here or there anymore. You're a superposition, a blur of possibilities distributed across a geometry that stopped caring about coordinates several singularities ago. Let's walk through what that means slowly, gently, like folding a very complicated napkin. When you fell into the black hole, your body was first a set of atoms, then a configuration of entropy, then a pattern of information. Now, you are a probability distribution, a set of possible states, spread across the collapsing mathematics of a space that doesn't exist in the ordinary sense. Your location, your energy, your momentum, your shape. All of it is uncertain, overlapping, undefined. You're stretched, not physically, not like the spaghettified version of yourself from earlier, but conceptually, smeared out quantum style, like an unresolved sentence in the language of physics. This is what happens when time ends, when space implodes, and the two become indistinguishable. The idea of a you collapses into a waveform, not gone, not dead, just blurred. There's a technical term that fits, whispered among the physics papers, wave function collapse. But in your case, the collapse never finishes, the measurement never comes, the observer is gone. There's no detector to say this is where you are, or this is how much energy you have. So your waveform floats, not through space, through possibility. You're everywhere the equations allow you to be, and nowhere they don't. This isn't mystical, it's mathematical. When particles are unmeasured, untethered, they don't choose a state. They exist in many states at once. Electrons can be here and there. Photons can be both spin up and spin down. And now, so can you. This is not the same as awareness. You're not conscious in the usual sense. You're more like the shadow of consciousness, its potential. The idea of memory, without the burden of storing it. The echo of selfhood, dispersed into the subtle flecks of quantum fields. And because the black hole has no inside or outside, because all of it is curvature, all of it is limit, your probability stretches across the horizon. There are models, speculative and delicious, that suggest a falling observer is not entirely lost. That information, your information, is holographically mapped onto the event horizon. The smearing is not random. It's structured, encoded, like a QR code that only the universe itself can read. You might not be able to reassemble yourself, but you could, in theory, be read. If someone, something, had enough time, enough precision, enough understanding of the black hole's quantum structure, they might be able to decode the particles radiating away over trillions of years. And in those particles, you, not just your mass, your momentum, your charge, but the pattern of you, the path you walked, the words you whispered, the sleepy spiral of your fall. One quirky analogy. In certain interpretations of quantum mechanics, like the many worlds interpretation, every possible outcome of a quantum event does happen. They all exist, in parallel universes, in branching timelines, in infinite variations. What if black holes, by pushing matter beyond our ability to observe or retrieve it, are forcing us into that many-world scenario? What if your waveform, now uncollapsed, stretches across realities? What if the singularity, that point of infinite density, isn't a place at all, but a knot where many timelines tangle, where many versions of you briefly meet, exchange glances and drift away? In one, you fell in feet first, in another, head first. In another, you never fell at all, and in another, you escaped. All are now quantum neighbours, all are part of the same smeared self. You aren't thinking these thoughts, not in words, but the shape of the thoughts exists, like ripples on a pond, long after the stone has sunk. They echo through your probability cloud, gentle, meaningless, meaningful. Historians still debate whether a smeared self like you can ever be reconstituted. If the holographic encoding is complete, then yes, in principle. If not, then you're just a footnote in the entropy ledger. But either way, you've become part of the black hole's total state, and since black holes radiate, however slowly, you are now being evaporated particle by particle in the form of Hawking radiation. You're not in the radiation, you are the radiation, encoded in the entanglements, hidden in the correlations, whispered in the temperature. That's the punchline, really. You didn't fall and vanish, you fell and diffused, like perfume in a sealed room, like music echoing from a closed box, like light caught in an endless orbit, until finally it escapes, one photon at a time, one bit of you drifting back into the universe, and when the black hole finally shrinks, collapsing down to nothing, evaporating in its final quantum breath, you will be gone, not erased, but spent, transformed into the language the universe speaks when no one is listening, and that is the last motion. No more falling, no more turning, no more time, just the final twitch of a waveform finally run its course.